Okay. I think for today's course, we're still in chapter 12. Hopefully, I can at least finish this either two or three sections in chapter 12. So the schedule will be so we still have next Monday, Wednesday. So probably today's is chapter 12. Next Monday is still maybe chapter 12 and maybe some exercise. Maybe 21 and 26 will be maybe 21 still some part of chapter 12 and reviewing the chapter 11, and 26 all will be reviewing chapter 10, 11, and 28 will be your midterm. Okay, so Wednesday will be your midterm. So your midterm is chapter 10 and 11. Okay, so I will provide a schedule for review chapter 10, 11 before the midterm, 21 and 26. Okay. So hopefully for today and next Monday and Wednesday, I can finish all the chapter 12. Okay. And after the midterm, maybe we will go into chapter 13. But I need also some quizzes, but maybe later, okay, after 1 or 2 weeks after maybe 2 weeks after the midterm, maybe a quiz. Okay, but I will let you know later. Okay. So let's continue on for course. So we are in a component of a factor. So to be familiarized, okay, I think you're already familiar with the factor. So every time you see a bracket with a like this, okay, it means it's a factor, and inside of that bracket will be a component of that factor, or component of x, y, and z. Okay. Now, aside from how the component works, we also have the length. Okay, so magnitude. So magnitude or length. Um, if v is a factor, usually the length we are using this symbols or these symbols. For example, if phi is a factor and the component of phi, or let me write in the terms of component factor, maybe phi1, phi2, the length will be the squared of f1 and plus f2 squared. This is in 2 dimensions. In 2 dimensions. In 3 dimensions, if you have 3 components, the same thing apply. and that will be your magnitude. Okay, so this 2 dimension and 3 dimensions. Okay, so that's the magnitude. Now let's move to uh, the property of vector. Okay, I think you're already familiar with the magnitude, right? Okay. Okay. So just a review. And to add the vector, let me write to add the vector with with other factors. For example, if A is A1, A2, and B is B1, B2. If you want to add this A plus B, then you can add each each component for X and for Y. Also happens for the subtraction. So that's what is happened, and also similar for 3D, 3-dimension factors. Okay. And if you have a constant scalar multiplied by the factor, then this is the scalar will multiply with each component. Okay, and also same thing happen in 3 dimensions. Okay, and the property, let's say if A, B, C vectors, so A plus B is B plus A, and most of the mathematical property, the factor is still follows that property. If they subtracted with itself, then it will be 0. Let's say if D is scalars, then and if this is D plus E and A is a factor, so dA plus EA. We multiply with the 1, so A. I think this is not a problem. Basically, it's similar with mathematical basic law. Okay, not really that complicated. Okay, now we also have, okay, aside from the property, we also have, it's called the standard, the standard basis vectors. It's usually with the word or the letter I, J, and K. So I is for the x-axis, J for y, and K is for the z-axis. So this is called the standard basis vectors. So they have length at least 1. Okay, so they have length 1, and direction, positive x, or positive y, or positive z. In 3 dimensions. Okay, in 2 dimensions only ij. Okay, so you look at these definitions. Let's say this is so this is j I k. Now if we have a vector a, let's say it's a1, a2, and a3, we can write this a as a1 let me resize this smaller, and plus a2 and plus 0, 0, a2. So we can write down this as the standard basis. Let me just write the all the things here. So A, we can write down A as A1I plus A2J plus A3K. I believe you are already seeing a lot of this IJK in physics, right? So that's the definition. So the IJK is actually standard basis vectors, which have each of them have a length of 1. Okay, and it's pointed to the positive x or positive y or positive z. It depends on this I, j, and k. Okay. So in summary, for example, you have 1, -2, and 6, or any value that you can think of in 3 dimensions. You can write this in terms of ijk. So I, and then -2j plus 6k. So from here, because we already know the ijk, what is for and what the definition is. In the next chapters, like in chapter 13, we will learn more, because in chapter 13 it's actually all the first calculus method, the basis method, like for differentiation, integrations. In chapter 13, all those things are still applied, but in the factors. So you will see the function itself in a factor forms. Okay? But how we deal with the factors is the same as we deal with our first calculus lesson. Okay? The difference is just the space, okay? And the how we deal with the factors. That's just the difference. All the things, how we derive, integrate, all the things still the same. Like arc length, blah blah blah, still the same. But the difference is we need to apply in a factor. Okay, that's the chapter 13. That's why we need to have the chapter 12 first, everything about the factors, and we can apply later in the chapter 13 and maybe a little bit in chapter 14. Okay. Okay, this is the standard basis factors. Other terms that are still related is a unit factor. By definitions, unit vector is a, let me write maybe factor whose length is 1. So basically, the I, j, and k, this is actually a unit vector because all have length 1, right? So basically, this is unit vectors. And in general, if the vector is not equal to 0, the unit vector that has same direction as the vector A itself is, let me use the other terms. Uh, let's use U as a unit vector. This is A divided by the magnitude of A. To confirm, well, it's like proving this. We can let some C is equal 1 over scalar A, the magnitude A. Then U will be CA, which means C is the scalar. It's scalars because it's magnitude. So the magnitude of U is a scalar of CA, or we can break down CA as C magnitude C and magnitude A. And we can look at C as 1 over A. which is equal 1 at the end. So we confirm that the unit vector is having a length, its length is 1. Okay. And I think in your textbooks there are some applications regarding physics, but I think I will not going into there. Yeah, I will not going to explain that, but all the formulations of a vector is based on what we have learned before. Okay, so that's the I believe that's still some intro of a vector. So after this, we will go to the dot product and the cross product. Okay, any questions? Any questions? Any questions here? I think it's all. I think you are already familiar with vectors, right? Let's move to the sections 12.3, the dot product. So 12.3 dot product. So what is the dot product? So if we have a vector, let's say we have a vector A and we have C, let's say this is a scalar, this is a vector, we can multiply this easily, right? But what if we have A and B and both are vector? What is the result? So this is the question for the dot product. So maybe I will start with the definition. So if a vector A is A1, A2, A3, and B is B1, B2, B3, then dot product of A and B is the number A dot B given by, this is the formula, A dot B, A1, B1 plus A2, B2 plus A3, B3. Sometimes the dot product is called scalar product or inner product because the result is a scalar. And it's still the same if you're having, because it's 3 dimensions. For 2 dimensions, still the same. Apply. So that's the dot product. Okay. Some property for the dot product. So if you have A dot A, which means it's multiplied by itself we can also say it's magnitude but squared. And you can have a dot b equal b dot a. There's not a problem because both have the same amount of value, right? Because you are just adding all the multiplications. And you have, if you a dot b plus c, you can a dot b plus a dot c. So if this is if a, b, c is vectors and d is scalar. So if you have dA, okay, you can exchange the scalar. If you have dA dot b, you can move out this scalar outside, or you can exchange with b. Not a problem, because the result of the dot product is a scalar, so there will be not a problem. And if you have 0, then it will be a 0, because you will multiply all components with 0, and the result will be 0. I think you can try the proof for this and this, or maybe this, but by yourself. It's not really difficult to prove. You can just try and put some value to A, B, and C and check the results. And sometimes the dot product is, let me write in the new section here. So if this is factors, and this is also a factor here, let's say this is A, this is B. And this will be A minus B, right? And sometimes we can also observe in geometric interpretations, we have angle theta between A and B, okay? So dot product A dot B, we can represent those dot product in terms of angle theta. So if this is O, this is A, this is B, yes, yeah, yeah, A minus B. Here, B is here, so here, right? Right? It's not like here. It's going there. So minus is here. So if we put minus here, If we put here, so it will going here, the same, right? Right. So let me write the theta. So if the theta is the angle between line segment OA and OB, so if factor A and B parallel, then the angle is 0 or theta equal pi, right? If both are parallel. So maybe if B here and A also goes here, then the angle can be 0 or it's 180, right? Now, from these conditions, then we can have the relations in terms of A dot B is the scalar of A, scalar of B, and then cosine theta. If we look at the triangle ABO or OBA, okay, let me write. Observe a triangle OAB. We can write if you remember, for triangle, so this is the law of cosine. So if you look at the triangle and we apply for looking at the AB squared, we can expand the formula for law of cosine. Okay, and now because we also relate all of this with the vectors, we change now this AB, OA, OB with our vectors. So this will be A minus B. Now A is the vector, B vector from what we have learned before. And then OA is A squared, OB is a B squared, and this will be minus 2 A, B, and cosine theta. Now, let's mark this as equation 1. Now we can also expand this A minus B squared becomes A minus B and A minus B. This is A dot A minus A dot B minus B dot A plus B dot B. Or we can set up the A squared minus 2AB plus B squared. This is the second equation. And let's put the second equation into the first equation. So it will be A squared minus 2AB plus B squared equal A squared plus B squared minus 2AB and cosine theta. So we can cancel this, and we will have only minus 2A dot B minus 2, the magnitude A, magnitude B cos theta. So we are proving our formula that A dot B is equal the magnitude of A, the magnitude of B, cosine theta. Okay, so uh, usually we get this formula just as it is, right? But if you want to look at into a clear details, you can look the triangles. Okay, if you have A, you have B, you can define in a geometric analysis using law of cosine, using the triangle, and you will arrive at the formula of dot product. Okay? And this is our conclusion for dot product. Okay? And from here, we can also write down the formula as a cos theta equal A dot B divided by the magnitude of A and magnitude of B. And theta, remember, theta is an angle between A and B, in between A and B. And we need to set up that the factors A, B is a non-zero factors. Because if it is zero, then we cannot apply all this formula. And theta is angle between A and B. I hope you don't mind. I'm writing the factors A, B just like that. But in the exam or midterm or exam, I will write the factors in a bold letters. Okay, so it should be bold A or A with the arrow. But since I will have trouble if I'm writing all the arrow and you cannot read the letters, so I'm just writing as it is. But in your textbook, I think you can see that the factors A is having a bold letters. Okay. Okay. And because we are now looking at the angle, so if okay, if let's say two vectors A and B are orthogonal if and only if the dot product is 0. Let me write the explanations here. Sometimes you can call the orthogonal as a perpendicular, same meaning. The angle between is pi over 2. Okay. The orthogonal is like this. Okay, wait. So when you dot or multiply these vectors, of course, because it's pi over 2, the cosine will be 0, which means the result will be 0. Okay. So whenever you find in your notes or text or a problem in the exercise, when you want to evaluate the perpendicular factors or orthogonal factors, A dot B should be 0. Okay. Okay. Now the next section, still in the dot product with some additional notes. It's called the direction angle. And direction cosine. So I need to draw a 3-dimension axis. Let's say it should be a rectangular object, but I think it's not really rectangular. But I hope you can see that this is rectangular. Okay, it's really bad. Let me point out the factor here. Let's say this is a factor. Maybe factor A. Okay. And in every part from all three axes, okay. If you see the factor A is going through this point in this rectangle, so it's going here. Okay, now the angle between this A and other axis, at least we will have three angles. Okay. The angle from X to A, the angle from Y to A, and the angle from Z to A. Okay, let's define all those three angles first. So first here is, let's say, alpha from X, and from Y it's beta, okay, and from Z is gamma. Okay. Okay, let me write some notes first, and we will go back to the picture. So direction angles of non-zero uh, factor A are the angles alpha, beta, and gamma that factor A makes with positive X, positive Y, and positive Z. And the second, the cosine of this alpha, beta, gamma are called direction cosine. So basically, it's the same thing. Direction angle is just its angle. Direction cosine is the direction of that angle. Okay. Now we can apply the each of angles. Let's say cos alpha is a dot. This I is just one unit length. So you will have a1 and divide by the magnitude of a. So in the picture, a1 is here. And the same thing in A2 and A3 in each of axis. Okay. So you will get the same or similar with other angles as well. And if we square all this alpha, cosine alpha, beta, and gamma, we can have these equations. Or we can write this in more efficient way. Just make it in a more simple. And from here, we can also write down that the unit vector, right? The unit vector is equal this. So this becomes the direction cosine. And the angles is direction angles. Okay. Okay, this is just I think in the applications, maybe you already use most of these vectors. But what I want to emphasize is the terms. Okay, so whenever you find like find the direction angles, blah blah blah, find the direction cosine, which means it's actually this angle. Okay, this cosine, which is alpha, beta, gamma, the angles from the vector and each axis, okay, each positive axis. Okay. Okay, that's the direction angles and direction cosines. Okay. So I think we can make it to the cross product, but maybe just an intro. But before that, let me go to the projections. It's called the projections. So still in the dot product, we have the projections. Oh, and by the way, I think in the early classes, um, do we have an agreement that I offer like two options? We have full course with break, 5 minutes, 5 minutes, or we have full course without break, but I will finish the class early, 10 minutes early, right? Okay, okay, early, right? Okay. So if you are maybe disagreed and want to have like full course with break until 3, maybe for today is 12:10, right? Should be 12:10. I think that's also fine if you want that. But if we do have like agreement in the class, like we have at least decisions that, okay, we have the options for without break, then I hope you don't fill in the survey that, oh, the class is short, okay? Because we do have an agreement, and by agreement means we all agree in the class. If you disagree, then you can say so in the class, okay? Yeah, it's not happened yet, but I'm just curious, okay, whether it will be that thing or not, okay? Okay, anyway, the projections, we have, let's say we have the factor A and factor B, and we have uh, coordinate P, Q, and R. So if I'm projecting the factor B, let's say going here, projecting to A, and let's say I have a new coordinate S in a segment of PQ, then this okay, this factor here uh, this is a projection of A to B. This means vector projection of B on A onto A. I will give you another example of this factor projections. Let's say you have another factor here. And let's say it's going here. And same, it's P, Q, and R. This is a factor A. This is factor B. Now, if we want to make factor projections of B on A, the same. If you want to make the same case with the left on this factor, the new factor here, so we can make it from here, from this B. Vector B is here, and we project to A. Okay, so we can make extensions in A here. Okay. Okay, that's the projection. Let's say this is a new point S, and this is the same projection vector projection B onto A. I need to at least pay attention to how it looks like in the terms. Okay, so this is projections of vector B onto A. Okay, yeah, sometimes I also confuse which part to project, but the official definition is projections B, the vector B on A, the vector B on A. Okay, but if you read like from left, oh, projection A onto B, sometimes you will be confused. But if you look at the figure, you will understand. Okay, you will understand. This is just a terms of how to write. Okay. So first, this is let me write in. So this is called the factor projection. Maybe I'll write the formula first, and the next one is the scalar projection. So the formula, factor projection of B onto A is projections and then the unit vector, and you can write A you will see the difference with the others projections. So this is the factor projection, which means you need to multiply with the unit vector. Which means this is actually the B cosine theta, right? In terms of the dot product formula. Okay. But the factor projections, you need to multiply with the unit vector of A. Okay. And you will see the difference with the scalar projections. You don't need to multiply with the unit vector. This is factor A, factor B, and similar. If we are want to projecting the B on A, we can do that also. And let's write a new point S here. And let's make a theta in between of A and B. And in this case, I will write the B cosine theta as the component of B along A. Now the difference between this and the previous picture is that this line, the red line here, is not a vector. So this is just a projection of the vector B onto A, but it's not a vector here. So we call this is a component of B along A. So this is not having any direction. So we only measure the length. Okay. So that's why I'm just writing B cosine theta. While in the projection here, in the vector projections, it's the same thing B cosine theta, but it has a direction. So that's why I need to multiply with the unit vector. So it has a direction. Okay, that's the difference. It's similar, but the difference is just the unit vector. Okay, so here you don't need to multiply with the unit vector. So this is the component. Okay, So actually, it's not too difficult. The difficulty is how to define these two. Okay. So we call this component, and this is equal a dot b just divided by the magnitude of a, and that's it. That's it. The only the length. We only care about the length for this part, and this is called the scalar projection. So maybe I'm giving you what example we can do from the scalar and vector, at least how to find and how to differentiate these two. Okay, let me write some questions here. So let vector A and B find scalar and vector projection. Uh, find scalar and vector projection of B onto A. Because it will be a different case if I'm switching A and B. It will be different. So meaning what you need to do is find the projection, or maybe the scalar first, the component of B along A, and projection of B onto A. Okay. From here, I think we can write the component. So A dot B divide the magnitude of A. So we can start to add the A dot B. So minus 2 plus 3 plus 2 divide by negative 2 squared plus 3 squared plus 1. So it will be 3 divided by square root of 14. And the projections will be the component multiplied with the unit vector. So this will be -3 divided by 7, because -2, right? 2, 14, yeah. And 9, 14, 3, 14. Okay, so I hope you get the idea for the projections, the component along factors, and the factor projections. Okay. Let me continue to some intro for the cross product. Let me see how much we have. I think application for projections mostly in physics, if you remember. So that's the projections. Let me just start with the 12.4, the cross product. Okay, if you have, let's say the factor A and factor B, the idea behind the cross product is actually if we can find a factor that is perpendicular to both A and B. So that's the idea of cross product. Okay, so remember that we have the idea of the right hand rule. So if we are having these two vectors, if we are trying to cross this, right? If you remember, then there will be a one vector that's perpendicular to both A and B. That's the idea. And how to produce such factor, we need the cross product. Okay, we need the cross product. So the idea is how to find a factor that perpendicular to factor A and factor B. So let me start with the cross product of two factors. So given two non-zero factors, and B, let's say we have two factors A and B, and suppose C, let's say C is also non-zero. Suppose non-zero factor C is perpendicular to A and B, and C is having a C1, C2, C3. Then A dot C is 0, B dot C is 0. Now we can expand and try to multiply and add all this dot product. So A1 C1 plus A2 C2 plus A3 C3 is 0. And B1 C1 plus B2 C2 plus B3 C3 is also 0. So to eliminate one of this, let me eliminate the C3. I will multiply this with the B3 and multiply this with the A3. So I will eliminate this, and we get A1, B3, and then it should be minus, subtract this. Okay. A1, B3 minus B1, A3, and this is C1 plus A2, B3 minus B2, A3. This will be C2 is equals 0. And if we see this form, we can conclude this actually C1 is actually the component of in the C2. So C1 is equal A2 B3 minus A3 B2, and C2 is A1 B3 minus A3 B1. Okay. And we have these equations. We put back these equations into the first and second equations. And we get C3 is A1 B2 minus A2 B1. Okay. So after substituting substituting C1 and C2 from original equation, or not from, to, onto original equation. Okay. And we get this C3. So we get C1, C2, C3. The factors is C1 is A2B3 minus A3B2. And C2 is A1B3 minus A3B1. And C3 is A1B2 minus A2B1. The results here, this is called a cross product of A and B, and usually denoted as A cross B. And notice that from here, the result is a factor, okay? Not a scalar, like a dot product. Dot product resulting scalar, but the cross product is another factor. To help you seeing the big picture of this cross product, let's go to the determinants. If you have order of 2, the determinant is A, B, C, D is AD minus BC, right? Now you can see what is happening here. The connections. It's something minus something, something minus something. Okay, it's actually related to what we call the determinants, and you can also use that for your notes. So if you have determinant order of 2, you have AD minus BC. If you have the order of 3, if you have order of 3, so A1, A2, A3, B1, B2, B3. So let me help you to remember. If you have order of 3, so if we start from, if you want to observe A1, A2, A3 in terms of in the format of a matrix, so A1 will be multiplied with the determinant in here. Okay. So B2, B3, C2, C3. And then it's minus. I hope you remember how it works. Okay. From the matrix definitions. And A2, this is B1, B1, B3, C1, C3, and plus A3, B1, B2, C1, C2. Okay. And remember, you can take A1, A2, A3 and put here, or you can take B1, B2, B3, or C1, C2, C3. The result will be the same. The result will be the same, the determinant. Let me write here B1, but this is minus, now it's plus, and minus. But if you want to simplify your understanding, you can just take out with the A1, A2, A3, it's still fine. If you want to make another B and C is also okay. But this equal this equal this, it's all the same. Okay. And usually, okay, in terms of vector, um, let me make some notes. This part here, the A1, A2, A3, usually we can exchange to just I, J, and K. So all this with it become I, J, K. Okay, it's also can be done. So we can write the A cross B. Let me write here. So A cross B. So I, J, K. And then this is A1, A2, A3, B1, B2, B3. Okay. So in terms of the cross product that we will going into more details, you can exchange this order of three, the top row here, with the IJK, with IJK. So you can write as this form here, or if I uh, write in terms of expansion, And maybe to conclude the cross product, we still have some parts for the cross product, but let me just write some theorem first. So the vector A cross B is orthogonal to both A and B. So how to prove that? We can compute the A cross B through our definitions with the order of 3 determinants. We can compute this, and then we can dot with A or dot with B. It should be 0. You can try by yourself. So you can expand this A cross B into this and write down the formula. Calculate all the determinants here. Calculate here. Calculate this also. And then you dot with A. You multiply with A. So A is A1, A2, A3. The result will be 0. Yeah, or you can also dot with B. The result is also will be 0. So let me write in terms of B. It's also 0. Okay. And therefore, it's orthogonal. Okay. So therefore, it's orthogonal. Okay. Another theorem, but I think I will explain more later, but I will write the theorem first. If theta is angle between A and B, so the angle is in between 0 and pi, then length of cross product A cross B. So the length, the magnitude, okay, is given by this with sine theta. I will explain why and how maybe later because we don't have really much time today. Okay. But I will write the theorem first, and later I will continue from here next Monday. Okay. Okay. Any questions? Any questions? If no, then I will stop here. Okay. Is that okay? We'll stop here and continue the cross product next Monday. Okay. So I hope all of these factors you can be more familiarized because we will use this in the chapter 13, and I think in the next year courses you will learn more some factors. Okay. So that's it for today. I hope you understand the concept.